Hello, welcome to my talk all about fluids. This talk is the first part of the talk on potential flows, with the focuses on the theory of potential flow. In this talk, I will tell you what are irrotational flows and where we can often see the irrotational flow. It has been proven by numerous examples that the fluid motion is universally governed by Navier-Stokes equation. Navier-Stokes equation is comprised of a continuity equation and three momentum equations. Here, the vector form of the moment equation is given. In this equation, we can see the substantial derivative is used for calculating the total acceleration of fluid, the local acceleration, the convective acceleration. The forces acting on the fluid include body force, for instance, the fluid gravitational force, the surface force due to the pressure gradient, and the viscous force. Navier-Stokes equation has four partial differential equations, one from the continuity equation and three from the moment equations for three velocity components. The governing equation could serve for four unknowns. There are three velocity components, u, v, and w, and the pressure, P. Therefore, the dynamic system for incompressible flow is perfect. However, solving Navier-Stokes equation is proven to be too difficult, if it is not impossible, because there are partial differential equations. There are nonlinear partial differential equations. The practical flows mostly involve in complicated turbulence, with eddies from very large, similar size as the fluid domain of interest, all the way down to the very small length scale, cosmograph length scale. For many practical problems, it might not be necessary to solve the four Navier-Stokes equation. Instead, for some flow, simplified method can be used to solve the problem. One famous class of the simplifications to Navier-Stokes equation is the potential flow theory, in which the flow is assumed as irrotational. Nowadays, the strict mathematical methods have been well advanced and established for such flows. For instance, the boundary element method, BEM, for wave structure interaction, the braid element method, another BEM method for fluid braid interaction. The methods based on the potential flow theory find a lot of practical applications. That's because they are reliable, they are fast, and accurate in many applications. For instance, the boundary element method is an industry standard for studying ocean platforms and wave actions. It is generally accepted that the potential flow is under the following three assumptions. The flow is irrotational. This is a must assumption for potential flow, since this assumption could lead a velocity potential function. The mathematical equation for this assumption is the core of velocity vector is 0. The flow is incompressible. This is acceptable for many practical problems for which the flow speed is not very large. The mathematical equation for incompressible flow is given by this equation. However, it must be pointed out that the compressible flows can be irrotational as well, but its dynamics would be much more complicated. The third assumption is the flow is inviscid. This assumption is acceptable when the corresponding Reynolds number is very large, as we see in many practical problems. The mathematical expression for inviscid flow is given by this. The fluid viscosity coefficient mu is 0. Then what is potential flow? Strictly speaking, a potential flow is an irrotational flow, and no more hypotheses are needed. For most practical problems, an irrotational flow might mean an inviscid flow, but they are not equal. I will make a talk on this topic in another talk. Therefore, the hypotheses of an incompressible and inviscid flow are generally needed to make the potential flow simpler. And all these hypotheses have worked very well for many practical problems. Then what is an irrotational flow? The definition of an irrotational flow is that the circulation of fluid velocity vector on an arbitrary closed curve is 0. The curve C here, and then the circulation gamma is given by this. If the circulation gamma is 0, that means the flow is irrotational. Using Stokes' theorem, we can have this mathematical equation. So this changes the circulation to the integration on the surface enclosed by the closed curve. This equation would lead another definition for the irrotational flow. The core of velocity vector is 0. In this slide, the physical meaning for an irrotational flow is explained. A rotational flow can be understood that the fluid element, the very small fluid element, rotates around its own axis when moving around the path, while the irrotational flow means that the fluid element does not rotate around its own axis when moving along its path. A more intuitive understanding of the irrotational flow can be analog to a Ferris wheel on which the capsules can be taken as the fluid element, and the capsules are hinged on the rotating wheel. When the wheel rotates around its axis, the capsules keep the upright positions all the time. People in the capsule can feel there is no rotating motion. The capsules moves very similar to the irrotational flow. The capsules move with the wheel, but not rotate around their own axis. Since each capsule has the same speed as the speed of the hinge, so this is very similar to the irrotational flow. A contrast is the horrible rotating wheel, on which the capsules are welded on the rotating wheel, and when the wheel rotates, the capsules move rigidly with the wheel. It would be in an upside-down position when it reaches the top. We can see that the velocities are different for different positions on the capsule, and the differences of the velocities on the capsule means the rotating motion around its own axis. This is very similar to the fluid rotational motion. In reality, how we can tell which is rotational or irrotational flow? Generally, we have two ways to check whether the flow is irrotational or not. The first one is for checking whether the core of the fluid velocity vector is zero. We need to check every point in the fluid domain to see whether the core of the velocity vector is zero. If not, then it is rotational flow. The second way is to make a closed curve, any closed curve in the fluid if you like, and check whether its circulation is zero. If it is not, then it is rotational flow. For instance, in the coiled flow in the plot, we can draw a rectangle and check whether the circulation is zero. Obviously, for the coiled flow, the circulation on the rectangle is not zero. Hence, the coiled flow is rotational. Now we look at where we can often see the rotational and the irrotational flow. For a uniform flow past a glass plate, due to the fluid viscosity, near the plate surface, there will be a layer where the fluid velocity increased from zero to the same velocity as that of the uniform flow. This layer is called the viscous boundary layer. If we extend the flow field more above the boundary layer, we can see the velocity distribution like this, and we can easily check in the boundary layer the circulation is non-zero here, so the flow in the boundary layer is rotational, and outside of the boundary layer the circulation of the fluid velocity vector is zero. Hence, it is irrotational flow. The other example is the flow coming from the large area into a contracted area. In the large area, because the boundary is far away the main flow field, so the majority of the flow in the large area is irrotational. And when the flow comes into the contracted area, because of the viscosity of the fluid, the flow might become rotational, as shown here. And when the flow comes out from the contracted area, the flow might become irrotational again. However, this is a simple example. Whether the flow is irrotational or rotational, even in the contracted area, is totally dependent on the Reynolds number. If Reynolds number is very large, and then the flow, even in the contracted area, could be irrotational. Another example is for the flow past an airfoil. The flow above the upper surface of the airfoil has a viscous boundary layer. Within the boundary layer, the flow is rotational, and the outflow is irrotational. In this slide, we are looking at the famous example, the flow in a horizontal pipe. So this is a very famous example in many textbooks. When the Reynolds number is less than 2,300, the flow in the pipe would be nominal, and then analytical solution can be found for such a simple flow. In the steady state, the flow has a parabolic velocity profile, and as such a case, the flow is rotational. We can easily check using the method presented previously. So this is the case we can take as the boundary layer is extended from the wall to the center line of the pipe. If we look at the development of the flow in the pipe, we can see at the inlet of the pipe, a large portion of the flow is rotational, as you can see here. And when the flow moves into the pipe, the flow, the boundary layers increase with the rotational portion decreasing accordingly. We can see the red lines here. In the fully developed flow, its velocity profile is parabolic, and the flow here is rotational. In the book of Selecting and adjusting boundary layer theory on page 95, it is suggested the solutions of Navier-Stokes equation in the entire flow field can be divided into two parts, as we can see the flow passing an airfoil. The outer flow, which can be regarded as an irrotational flow, and the flow can be studied using the potential flow theory, and the flow within the thin layer close the body or wall, as well as the wake behind the body, where the fluid friction is important, and therefore the Navier-Stokes equation must be solved. Prandtl introduced the frictional layer as the boundary layer in 1904. The concept of the boundary layer is very important for solving many practical problems, since the potential flow theory cannot deal with the problem of fluid friction. While solving the Navier-Stokes equation in the entire fluid domain is difficult. Nowadays, the boundary layer modeling is still very important in CFD modeling, which is very challenging for many practical complicated problems. For the flow in a horizontal pipe, when the Reynolds number is large, say 10 million, and then the flow profile would be a shape like this. So the flow in the pipe is fully turbulent. The majority of the flow field is irrotational, and the small area near the pipe wall are rotational region here and here. So when the Reynolds number becomes larger, the boundary layers would become smaller. As a result of that, the entire flow in the pipe can be approximated by an irrotational flow. For the irrotational flow, the core of the velocity vector is 0. This means this determinant is 0. And this corresponding to an equation as this. To make sure the equation satisfied, all the components along the three directions must be 0. Hence, we have three partial differential equations for the fluid velocity component. as this. So based on the hypothesis of irrotational flow, three velocity components are no longer independent of each other. They linked with these three equations, and it seems we can solve the flow field using these three partial differential equations. However, if we look at the 2D irrotational flow, from the zero core of the velocity vector, we can only get one partial differential equation as this. So for 2D irrotational flow, there's only one equation for two velocity components. Obviously, we need another equation for completing the system. Superficially, we can see there is a conflict in 2D and 3D cases. Since the 3D case seems a closed system, while the 2D case is not. Is this true? Or why we have such a conflict for 2D and 3D cases? The answer is that in the 3D cases, the three equations derived from the zero core of velocity vector are not independent of each other, because we can use any two equations of this to derive the third one. For instance, we take the first two equations and then differentiate the first equation with regard to x, and the second equation with regard to y. We have equation as this. Equaling these two equations, we have equation as this, and then we have the equation like this. So we can get an equation like this one. When we take the special case for this equation, c equals 0, then we have the exactly same equation for the third equation. So this explains these three equations from the assumption of an irrotational flow are not independent of each other. And that's why we need another equation for completing the dynamic system in 3D cases. This is the same as in 2D case. And it will be seen that the additional equation is the continuity equation. For the potential flow, the hypothesis of irrotational flow means a guarantee of a velocity potential function phi, and the fluid velocity vector can be simply given as this. So if the velocity vector is calculated from the velocity potential function, then its core is guaranteed to be 0, since we have equation as this. In the Cartesian coordinate, three velocity components are given as u, v, and w. Calculate using the velocity potential function as this. For the potential flow, in most applications, the fluid is also assumed as incompressible. This is true for many practical applications. For the incompressible flow, its mathematical expression is given by the divergence of the velocity vector is 0. Applying the potential function to the continuity equation, it leads to the Laplace equation. In details, the Laplace equation can be written in this form. As such, the problem with the three velocity components degraded into one scalar potential function phi In 2D, the Laplace equation can be rewritten in this. To solve the Laplace equation, the partial differential equation, we need to specify the relevant boundary conditions. It is interesting to notice that we haven't used Navier-Stokes equation or Euler equation in the irrotational flow yet. Since here, we only apply the conditions of an irrotational flow and the incompressible flow. The equation for the velocity potential function can be already established. Does this mean we can get the flow field without applying Navier-Stokes equation or Euler equation? The answer is no, since when we solve the potential function, we need to specify both kinematic and dynamic boundary conditions, but the dynamic boundary condition must be based on Navier-Stokes or Euler equation, or more specifically, the Bemoulli equation, which is the integral form of Euler equation. We have two different types of the boundary condition, kinematic boundary condition and dynamic boundary condition. The kinematic boundary condition specifies the velocity of the fluid on the boundary, such as the non-penetration condition, as the normal velocity of the body surface and the fluid motion are same, given by this. In irrotational flows, the no-slip condition is not applicable. Here, n is the normal vector, v is the body motion velocity. For a fixed boundary, v is 0. The second boundary condition is the dynamic boundary condition, for which the force acting on the boundary is specified. However, for irrotational flows, there might be fewer conditions to impose, since there is no shear stresses acting within the flow. The most applied dynamic boundary condition would be the free surface condition, for which the pressure at the water side at the free surface must be same as the air pressure at the free surface. In this slide, a simple example for the flow in a horizontal pipe is considered. Now we assume the flow in the pipe is irrotational, and we will compare the irrotational flow and the viscous flow in the horizontal pipe. Based on the problem analysis in the horizontal pipe, we can see the velocity component v and w about 0. So the Laplace equation is reduced to this simple equation, since the velocity component v and w are 0, and the solution for the velocity potential function is given by this. So the velocity component u can be calculated as this. Plot the irrotational flow profile and compare to that of viscous flow. We can see the irrotational flow is uniform flow in the pipe, while the nominal viscous flow is parabolic. The third assumption for the potential flow is the inviscid flow. Thus, Navier-Stokes equation is reduced to Euler equation with the fluid viscosity coefficient mu assumed to be 0. If we take the body force as the fluid gravitational force, for irrotational flows, we can use the velocity potential function to replace the velocity and use the vector calculus identity here, and we have this and this. So put all this together, we will have an equation as this. Based on the Euler equation, the irrotational flow and the conservative body force, we can obtain the Bemoulli equation, which is the integral form of the Euler equation as this. This is the unsteady Bernoulli's equation for irrotational flows. And this unsteady Bernoulli's equation can be very useful in some applications, for instance, in ocean wave theory. This unsteady Bernoulli's equation can be also written as this. If for a steady flow, a conventional Bernoulli's equation can be obtained as this. So we can see there might be different form for Bernoulli's equation. However, as a basic requirement, the Bernoulli's equation is satisfied under the following combined condition 1, 2, and 3, as the flow should be inviscid flow, and this is necessary for general form of Bernoulli's equation. The body force must be conservative. For instance, the fluid gravitational force is a conservative force. The flow is irrotational flow for both steady and unsteady flows. Or, on the flow streamlines, this is only for steady flows. And we have shown this in the talk of Euler equation. Similar to the irrotational flow, in which we introduce a velocity potential function, here, if an incompressible flow is studied, we can introduce a stream function, a vector, psi, as this. So the velocity vector is calculated at the core of the stream function. And because the stream function, the divergence of velocity vector is 0. This is an incompressible flow. It can be seen the stream function is still a vector with 3 independent components. Thus, generally, the stream function does not provide much advantage over the velocity vector in most cases. However, stream functions can be very useful in 2D cases. Generally, for the stream function, it should have 3 components as a normal vector, as this. However, in 2D, we take the velocity component W0. This means that the stream function should have only one component, as this, the scalar psi, to define the velocity component u and v as these equations. Now consider the streamline equation given by this, and write the equation into this. Combine this together, we can get the equation as this. This means the differential of the stream function on the streamlines is always 0. It means the stream function is a constant on a given streamline. And this is the main reason why it is called as the stream function. Another interesting fact is that in 2D, the dot product of the gradients of the potential and the stream functions are zero at this. This means that the fluid stream lines are perpendicular to the equipotential lines, as we have seen in many examples.